page 102 to 105, the relationship between continuity and differentiability. In this lesson, our goal is to establish a relationship between a function being continuous at a value of x and a function being differentiable at the same value. In other words, if a function is continuous at a particular value of x, does that imply that it is also differentiable? Or if the function is differentiable, does that mean that it must also be continuous? We're going to investigate these three functions. The first function we want to consider f of x equals square root of x squared minus 4 at x equals 2. So on the grid to the right, we want to sketch a graph of f of x from your graphing calculator. So if I were to graph f of x on my graphing calculator, the sketch would look something like this. Those two sides to be a little bit more equal, but you get the gist. Based on the graph, is f of x continuous at x equals 2? So if we remember continuity, right, there are three things that need to be true. The first is that the point must exist, right? So does f of 2 exist? It is defined and f of 2 is equal to 0. The second that must be true is the limit from the left must equal the limit from the right. So the limit x approaches 2 from the left of f of x is equal to, there is no left of 2 for the graph to approach, so this does not exist. And the limit as x approaches 2 from the right of f of x is equal to 0. So the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right of f of x. Therefore, the limit as x approaches 2 of f of x does not exist. And if the limit doesn't exist, then f of x is not continuous at x equals 2. Now we want to find the derivative of f at 2. Okay, so we could do this a few ways. One way you could do it is plugging this into a calculator, like we've practiced, to find our answer. I'm going to do all the work out so that you can understand and see how the derivative is found. So our function is f of x equals, I'm going to rewrite this function as x squared minus 4 all to the 1/2. Therefore, the derivative of x is equal to 1/2 squared minus 4 to the negative 1/2 times 2x, because this is chain rule to find the derivative. The 2's will cancel here, so then the derivative of f of x is equal to x over square root of x squared minus 4. So then f of 2, f prime of 2, prime of 2 equal to 2 over square root of 2 squared minus 4 equal to 2 over square root of 0, which is undefined. So since f of x, since f prime of 2 is undefined, f of x is not differentiable at x equals 2. So let's move on to the next page. Now we have a new function, x to the 1/3 plus 2, and we want to find the continuity at x equals 0 and if it's differentiable at x equals 0. So first thing we're going to do is we're going to sketch this graph. So I'm just going to sketch it really quickly using a few points that I know exist. It's a really bad sketch, but let's see if I can make it a better sketch. That's as good as it's going to get for now. All right. So at x equals 0, we know that to find continuity, we need to prove that it's defined. So f of 0 is defined. F of 0 equals 2. The limit as x approaches 0 from the left of f of x equal to 2, and the limit as x approaches 0 from the right of f of x is equal to 2. The limit as x approaches 0 from the left of f of x equals the limit as x approaches 0 from the right of f of x. Therefore, the limit as x approaches 0 of f of x exists. So then our third rule is, does number 1 equal number 2? And we know that f of 0 equals 2, and the limit as x approaches 0 of f of x equals 2. Therefore, f of x is continuous at x equals 0. So then the last thing we need to do is find the derivative. And again, you could plug this into the calculator. I'm going to do it out. So f of x equal to x equals 1/3 plus 2. So the derivative of x is equal to 1/3 x to the negative 2/3. So if I rewrite that, the derivative of f of x is equal to 1/3. So 1/3 cubed root of x squared. So f prime of 0 equal to 1/3 cubed root of 0 squared, which is just equal to 1/0, which is undefined. Okay, so in this case, since f prime of 0 is undefined, therefore f of x is not differentiable at x equals 0. And by looking at the graph, right, an undefined slope is also considered a vertical tangent, right? So this is a vertical tangent. If I had graphed it a lot nicer, you would have seen that it's a vertical tangent. So this is a vertical tangent at 0. And so we also consider this, another word for this is a point of inflection. Okay, and point of inflection is when a graph changes from one concavity to another. So this was originally concave up, and then it changed to concave down. So because it changed concavity, that's also considered a point of inflection, which is a vertical tangent, which means that we are not differentiable at that point. The last graph and function we're going to look at is f of x equals x to the 2/3 plus 2. So a sketch of this graph looks like kind of like a butterfly or a bird of sorts. So to find continuity, again, we need to make sure that f of x is case 0 exists, right? F of 0 is equal to 2, so f of 0 is defined. Second thing we want to check is the limit. So the limit as x approaches 0 from the left of f of x equals to 0, and the limit as x approaches 0 from the right of f of x is equal to 0. So the limit as x approaches 0 of f of x exists. And then the third thing we want to check is, does the point equal the limit? And in this case it does, because, oh wait, sorry, I am so mistaken. That is equal to 2 and 2. The limit's equal to, not 0. I'm sorry about that. So in this case, f of 0 is equal to 2, and the limit as x approaches 0 of f of x is equal to 2. Therefore, f of x is continuous at x equals 0. Okay, so now we want to find the derivative and see if it's differentiable at 0. So again, you could plug this into a calculator. I'm going to do it out. So we have f of x equals x to the 2/3 plus 2. F prime of x is equal to 2/3 x to the negative 1/3 plus, oops, not plus anything. So then f prime of x is equal to 2 over 3 square root of cubed root of x. So then f prime of 0 equal to 2 over 3 cubed root of 0, which is just 2 over 0, which is undefined. So f prime of 0 is undefined. So f of x is not differentiable at x equals 0. Okay, and the reason for this, if you look at the graph, is because we have this cusp here. So we call this a cusp, right? So there's a sharp turn, right? A sharp point, sharp end on our graph at x equals 0. So because this has a cusp, the function will not be differentiable at that cusp. So on this page, you'll notice that both functions were continuous, but neither one was differentiable at that point. So if we move on to the next page, we can look and state a few things. So the first thing we can state is that continuity does not imply differentiability. Because at a point of inflection, or a cusp, the graph is continuous, but not differentiable. Okay, and then the second piece of information is that in order for a function to be differentiable, it does need to be continuous. So in order for a function to be differentiable at an x value, the function must be continuous. Okay, so it doesn't need, so continuity does not imply differentiability. Just because a function is continuous at a value does not mean it's going to be differentiable. However, if a function is not continuous at a value, you can state that it will not be differentiable. Okay, so in order for a function to be differentiable at a value of x, the two things that must be true are f of x must be continuous at x equals a, and bringing it back to limits now, the limit as x approaches a from the left of f prime of x must equal the limit as x approaches a from the right of f prime of x. So this piece here deals with the point of inflection and the cusp. Okay, so if number 2 is not true, that means you either have a point of inflection or you have a cusp. All right, so let's look at this piecewise function here. We're going to do 2 more problems. So looking at this piecewise function, we want to consider g of x and see if g of x is continuous at 3 and if g of x is differentiable at 3. So if g of x is continuous at 3, then first thing must be true is g of 3 must be defined. So g of 3, we're going to use that first function, is equal to 3 plus 1, which is equal to square root of 4, is equal to 2. So g of 3 is defined. Second thing that must be true is the limits, right? So the limit as x approaches 3 from the left of g of x is equal to square root of 3 plus 1, which we just found to be 2. And the limit as x approaches 3 from the right of g of x is equal to 5 minus 3, which is equal to 2. So the limit as x approaches 3 from the left of f of x, of g of x, sorry. So used to f of x, of g of x is equal to the limit as x approaches 3 from the right of g of x. Therefore, the limit as x approaches 3 of g of x exists. And the last piece of information is that g of 3 must equal the limit as x approaches 3 of g of x, which it does. So therefore, g of x is continuous at x equals 3. Now to prove differentiability, right, the first thing we need to prove is that we're continuous at x equals 3, which we did in the first piece. So g of x is continuous at x equals 3. Now the second thing we need to see is the limit as x approaches 3 from the left and the right of the derivative of g. So one thing we want to do is first find the derivative of g. So g prime of x is equal to, and in order to do that, we're just going to find the derivative of both pieces of that piecewise function. So we know that we can rewrite the square root of x plus 1 as x plus 1 to the 1/2. And the derivative of that would give me 1/2 x plus 1 to the negative 1/2 times 1, because again, we need chain rule. and that's only when x is between 0 and 3. And then we have the derivative of the second one, which the derivative of 5 minus x is just going to be negative 1. And that's when x is between 3 and 5. All right, so then we can rewrite this to be 1 over 2 root x plus 1 when x is between 0 and 3. And then negative 1 when x is between 3 and 5. So then the limit as x approaches 3 from the left of g prime of x would be equal to 1 over 2 root 3 plus 1, which is equal to 1 over 2 root 4, which is just going to be 1 over 4. And then the limit as x approaches 3 from the right of g prime of x is going to be just equal to negative 1. And since the limit as x approaches 3 from the left of g prime of x does not equal the limit as x approaches 3 from the right of g prime of x, g of x is not differentiable at x equals 3. Okay, so moving on to the last page, I'm only going to do one problem on this last page. Both of them deal with finding the two missing variables that will make the function both continuous and differentiable. So first thing I'm going to do for h of x, because that's the problem I'm going to do. So for h of x, I know that in order to find differentiability, I'm going to need to eventually know the derivative. So I'm just going to do that now. I'm going to find the derivative of h of x. So I can rewrite this piece as k times x plus 1 to the 1/2. And so the derivative of h of x is going to be equal to 1/2 k x plus 1 to the negative 1/2 times 1. And that's where x is between 0 and 3. And then the derivative of the bottom is just going to be m, and that's when x is between 3 and 5. Okay, so now that I know the derivative of h of x, I can now look at the continuity and look at the differentiability to figure out what k's and what m's must be. So if h of x is continuous, then the limit as x approaches 3 from the left of h of x must equal the limit as x approaches 3 from the right. Okay, so we're going to set those two things equal. So we have k square root x plus 1 is going to be equal to mx plus 2. So we're going to plug in 3 because we're looking for the limits at 3, right? So we'll plug in 3. We have k square root of 3 plus 1 equal to m times 3 plus 2. So we have 2k equals 3m plus 2. Okay, so that's as far as we can go there. Next side we're going to look at is the differentiability. So if h of x is differentiable, then the limit as x approaches 3 from the left of h prime of x should equal the limit as x approaches 3 from the right of h prime of x. So we'll set those equal to each other now. So we have 1/2 k. Let me write this out. So we have 1/2 k 3 plus 1. Oops, before I put the 3. X plus 1 to the negative 1/2 equals m. Now we can substitute 3. We have 1/2 k 3 plus 1 to the negative 1/2 equal to m. And when we do that out, we get 1/4 k is equal to m. So now that we know m, we can plug that into this function here. So we'll have 2k equals 3 times 1/4 k plus 2. So 2k equals 3/4 k plus 2. And then just solve for k. So 5k, so 5 over 4k equals 2. So k is equal to 8 over 5. And then we can plug that into here to figure out my m. So 1/4 times 8 over 5 is going to be equal to m. So m is going to be equal to 8 over 20, which is just 2 over 5. Alright, so I want you to try that bottom problem on your own. For what values of a and b will the function below be differentiable at x equals 1? Try that problem out on your own and see if you can figure it out.